So we see that as a dynamical system scales up, and the processes of irreducibility and entropy creation operate in time, holistic strong emergence becomes a dominant force in the causal structure of that system. But does that signify the end of reductionism? Remember that these high-level processes are the intricate informational systems that are adaptive dissipative systems, increasing entropy in the universe. But in order for these adaptive dissipative structures to maintain stability far from equilibrium, they need to extract usable energy from the environment. As increasingly complex systems emerge within an open environment, thus creating an ecosystem, evolutionary energy niches emerge. These niches, in turn, give rise to new organisms that evolve to exploit them. The theoretical biologist Stuart Kauffman has advocated his notion of the adjacent possible, in which the environment creates its own niches for which it evolves into, but he's been unable to demonstrate how this occurs. This theory of random strong emergence, however, provides a framework for understanding how such evolutionary niches come into existence and how complex systems evolve to inhabit them. In biology, even the simplest biological and chemical systems contain an internal model of their environmental niche. This internal model enables the system to extract energy from its environment by predicting or understanding how to exploit low-entropy energy sources. For instance, in a simple chemotaxis system, an entity can move toward or away from positive or negative energy substances by constructing a model of the outside world using sensing mechanisms, gradient detection, signal transduction, and similar processes to maintain its far from equilibrium state. But what exactly is this model? It's a reductionistic model based on axiomatic foundations, though not explicitly as in a formal logical system, that predicts how the world works in that particular region of space. The more internal components that can represent information within the system, the better it can predict the external world. Examples of this include organisms such as the C. elegans worm, a mouse, or a primate, all of which have increasingly sophisticated internal models that allow them to navigate and adapt to their environment effectively. These internal models function as reductionistic theories of how the world works, enabling the system or organism to quickly calculate what will happen in the world so that it doesn't have to wait for the world to evolve and then determine its course of action. The system or organism can proactively use that shortcut to extract energy more efficiently than another dynamical system existing in the same ecological niche. And in accordance with Landauer's principle, these internal models are informational structures encoded in physical matter, and their working relationships with each other constitute the system's predictive capacity. Therefore, as the complexity of the dynamical system increases, the internal world model can expand, meaning that the explanatory theory can account for and predict a larger range of phenomena. In this manner, the scope of reductionism explanation is relative to the system or organism in which the model resides. Slices of the world can be reduced depending upon the complexity of the modeling system. However, there is a limit to reductionism's explanatory domain or range. Since the information is encoded in the physical components of a dynamical system or organism, there is a computational limit to what can be modeled. This idea is captured in Ashby's law of requisite variety, stating that, in order to deal properly with the diversity of problems the world throws at you, you need to have a repertoire of responses which are at least as nuanced as the problems you face. Another way to express this is that a system has a fundamental limit as to what it can understand or explain. It's as though dynamical systems and organisms possess flashlights to pierce the darkness of ignorance with beams that have varying but finite luminosity, proportional to the emergent complexity of that system. As such, reductionism's explanatory efficacy will always be required at various scales and slices of the universe. In this strong emergence framework, reconsider the cellular automata of Chapter 3. Suppose we have constructed a multi-billion parameter large language model in a Turing machine, which in turn is implemented on a Rule 110 cellular automaton, and we intend to understand why one particular cell is activated on the nth step of this cellular automaton. If our laws are the high-level supervenient Turing machine rules, then why one particular cell is activated will likely appear to be random in the same manner that a particular nitrogen molecule happened to glance off a surface in a random direction and with a random momentum. As we delve more deeply into the low-level cellular automaton cell activations to understand why this particular cell is activated, we could painstakingly delineate the full n steps, but in so doing, we would lose the ability to see the higher-level laws, the gliders and spaceships, or the even higher-level grammatical laws that the LLM observes when generating sentences. At the low-level subvenient description of the cellular automaton, the operations may be below a phase transition, and thus it might even be impossible to understand the upper-level emergent processes on the other side of that phase transition boundary. We would fail to see the forest for the trees, as it were. In order to provide a comprehensive explanation for the cell's activation, we must capture into working memory every cell activation in the causal chain leading up to the cell in question, and in so doing, the computational capacity would exceed that of the original system, thereby causing the higher-level features to vanish, in the words of Laughlin. It's as if there's an uncertainty principle in effect. The more one learns of the lower-level properties, the less one learns of the upper-level properties, and vice versa. This is analogous to trajectories in space-time allocating their energy budget to either traversing space by increasing velocity or maximizing proper time by remaining stationary relative to other frames. In this scenario, computational resources can be treated as trajectories through a two-dimensional space, whose axes are low-level description versus high-level description, instead of space versus time. Thus, phase transitions likely signal a new random emergent law, and as observed previously, the random nature of the new law presents a boundary for the reductionistic explanation. Depending upon what feature of the system is under investigation, we should choose the appropriate explanatory framework that best captures the predictive and explanatory behavior for that scale. For example, quantum chromodynamics, algorithmic information theory, general relativity, etc. It is important to recognize that there is no definitive way to determine whether a reductionist theory has reached the full breadth and depth of its potential scope. According to the undecidability results of Church and Turing, the provability of a postulate from lower-level axioms may be inherently unknowable. This means that the search for necessary and sufficient laws in an explanatory theory relies on creativity and ingenuity, a pursuit as much an art as a science. Yet, it is entirely possible that certain postulates or phenomena resist derivation from foundational principles, not due to a lack of effort, but because they are fundamentally unprovable. This inherent uncertainty drives the perpetual quest for the most effective explanatory framework, the never-ending reductionistic quest.